For over a century, physicists have been intrigued by the idea of black holes, with the concept gaining popularity around 1916. These cosmic anomalies include some of the most captivating and enigmatic phenomena we know. Sitting at the convergence of enormous gravitational forces and an unusual disappearance from our understanding, a black hole, potentially weighing as much as 2 to 4 million times the mass of our Sun, continues to be an enigmatic presence. In spite of decades of intense research, our comprehension has improved from almost no knowledge to piecing together ever more information. New discoveries made recently, such as Yakubu's breakthrough, have revealed startling insights about the interior of black holes. These findings may challenge long-held beliefs and provide new perspectives on the nature of these celestial bodies. This new information opens the door to more in-depth investigations into what might have been overlooked until now. Join us as we venture further into the fascinating world of black holes and uncover what's hidden within. The universe is vast and awe-inspiring. But before we begin, what exactly are black holes? To examine the most recent findings by Yakubu, it's essential to revisit the basic comprehension of black holes. While most of us have at least a general sense of what a black hole is, there are still a few important aspects that remain unclear. In Einstein's groundbreaking work from 1916, the theory of general relativity predicted the existence of black holes. At that time, the idea was merely theoretical. It wasn't until about 50 years later that evidence was found to support the existence of actual black holes in space. This revelation came in the 1960s during studies of the star X1, a luminous celestial body that emits X-rays. According to observations, these X-rays were not just moving at random but were being pulled into an invisible, dense mass. This mass, later identified as a black hole, changed our perception of the cosmos. The discovery was monumental, as it demonstrated that black holes were not figments of Einstein's imagination but tangible, elusive entities that warranted further investigation. Following this revolutionary discovery, scientists worldwide began a concerted effort to uncover more about black holes. Their efforts led to the realization that the Milky Way alone may host around 100 million black holes. However, due to the challenges in detecting them, this estimate remains imprecise. Even though black holes are incredibly difficult to pinpoint, scientists believe that millions of these massive entities are hidden within our galaxy, making it even more crucial to understand them. Let's break down the core concept: gravity. Black holes exert such immense gravitational forces that anything entering their territory faces a singularity, the point at which the rules of physics as we know them cease to function. Or, to put it another way, black holes are like gigantic vacuum cleaners pulling everything into them. One of the most terrifying aspects of studying black holes is the idea that if someone were to fall into one, they would gradually expand and become a unique entity. Their body would be torn apart by the intense forces of gravity before the point of total destruction. It's best to avoid getting too close to one, though they are scattered across the universe. Despite the nearest black hole being nearly 500 light-years away, the proximity still raises legitimate concerns. In 2021, scientists reached an important milestone by capturing the first clear image of a black hole, the M87 black hole. This achievement was the result of numerous nights spent aligning and taking pictures to produce a single cohesive image. Researchers gathered more data as they went and were able to discern that black holes comprise 3 different layers, contrary to the common belief that they are nothing more than endless voids. The first of these layers is called the event horizon, which marks the point beyond which nothing can escape. Once something crosses this line, it is drawn inexorably toward the black hole. The second layer, known as the photon sphere, is where light itself gets trapped, unable to escape due to the powerful gravitational forces at play. The final point is the singularity, where all matter is compressed into an infinitely small point, a place where the very fabric of reality collapses and all known laws of physics break down. What's even more intriguing is that each black hole is unique in its own right. While they follow the general 3-layer structure, the way they behave can vary significantly. This makes them particularly challenging to study, as conventional scientific methods don't apply. To study black holes, scientists must investigate these anomalies through indirect means, such as observing the radiation emitted from them or analyzing the gas and dust swirling around them. Directly inserting a probe into a black hole is futile, as anything that crosses the event horizon is drawn toward the singularity, where it is crushed into nothingness. This unavoidable fate means that billions of dollars cannot be spent on probes that would meet their end before offering any valuable data. Consequently, black holes remain the focus of theoretical and observational research. Adding to the complexity of black hole research is the fact that no 2 black holes are identical. When studying them, we must account for the breakdown of the laws of physics as we know them. Theories about the origins of black holes suggest that they could emerge from massive stars collapsing in on themselves. As a star burns through its fuel, it can no longer produce enough energy to counterbalance the inward pull of gravity, leading to its eventual collapse into a black hole. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. To further comprehend the characteristics of black holes, scientists from NASA focused on the M87 galaxy. There, they observed a powerful whirlpool of hydrogen gas spinning at mind-boggling speeds of 1.2 million miles per hour. The effect of centrifugal force should have torn the gas apart, but instead, it remained intact, indicating the presence of a massive object at the center, likely a black hole weighing up to 3 billion times the mass of our Sun. Another important theory was proposed in 1963 by New Zealand mathematician Roy Kerr, often misspelled as Royer, who used Einstein's equations to describe the behavior of rotating black holes. He argued that rather than collapsing into a single point as previously thought, a rotating black hole forms a structure known as a thin ring, or ergosphere. This rotating disk of matter is essential to comprehending the breakdown of physical laws in the vicinity of black holes. Additionally, Kerr's model anticipated the existence of a theoretical Einstein-Rosen bridge, wormholes, that could provide a shortcut through space-time, connecting distant regions of the universe or even parallel universes. As our observational tools and theoretical models evolve, so too does our ability to peer deeper into the cosmos and into the secrets that black holes may conceal. One of the most tantalizing possibilities is that black holes could hold the key to understanding the origin and fate of the universe itself. Some researchers have proposed that the singularity at the heart of a black hole may not be the end, but rather a beginning, potentially birthing a new universe through a process still unknown to science. This concept, sometimes referred to as a black hole cosmology, suggests that each black hole could be a gateway to a separate, self-contained universe. If true, this would imply that our own universe may have originated from such a singularity, an idea that radically shifts our cosmic perspective. Moreover, ongoing studies into the concept of Hawking radiation, proposed by physicist Stephen Hawking, challenge the once accepted idea that nothing can ever escape a black hole. According to Hawking, black holes may emit radiation due to quantum effects near the event horizon. Over time, this radiation could cause a black hole to gradually lose mass and eventually evaporate entirely. This theoretical process introduces a paradox that continues to puzzle scientists. If a black hole evaporates completely, what happens to the information it once held? This information paradox strikes at the heart of physics. According to quantum mechanics, information cannot be destroyed. Yet, if black holes eventually disappear and take all their contents with them, it would violate one of the most fundamental laws of nature. This conundrum has sparked debates for decades and has inspired new lines of inquiry into quantum gravity and the very structure of reality. In recent years, scientists have explored the possibility that information might be preserved on the event horizon itself, encoded in a faint, two-dimensional surface, much like a hologram. This has led to the development of the holographic principle, which posits that everything within a volume of space can be described by information encoded on its boundary. If proven true, it would revolutionize our understanding of black holes, space-time, and the fabric of the cosmos. At the intersection of quantum theory and general relativity lies the future of theoretical physics, a future that may finally yield the elusive theory of everything. Black holes, wormholes, and the mysteries they conceal are not just distant astronomical phenomena, they are laboratories of extreme conditions, where the rules of the universe bend, twist, and sometimes break. As we stand at the edge of human understanding, one truth becomes clear. The more we learn about black holes, the more we realize how little we know. Yet this humbling realization is not a setback, it is an invitation. An invitation to keep exploring, questioning, and reaching for answers in the darkest, most mysterious corners of the universe. Because, perhaps, hidden within those cosmic shadows lies the next great breakthrough, one that could change not just our science, but our place in the cosmos forever. The universe, continuing from where we left off. The pursuit of superstring theory and other theories that aim to unify nature's forces is an ongoing challenge, but it has the potential to unlock new insights into the very nature of reality itself. These hypotheses propose that the universe is composed of more than the familiar three dimensions of time and space. In point of fact, they imply that there are additional dimensions, but they are so minuscule and compact that they are beyond our direct observation with today's technology. However, their existence may hold the answer to comprehending phenomena such as black holes, wormholes, and the deepest mysteries of the cosmos. The superstring theory of the universe provides a fascinating picture, proposing that all matter and forces are manifestations of tiny vibrating strings. These strings are capable of vibrating at various frequencies, with each vibration corresponding to a different particle, just as a guitar string can produce different notes depending on how it vibrates. The basic components of nature may correspond to various vibrational patterns of superstrings. If proven, this theory would not only provide a unified explanation for the fundamental natural forces, like gravity, the strong nuclear force, the electromagnetic force, and the weak nuclear force, but also open up completely new methods of understanding the universe's structure. This could potentially provide answers to some of the most pressing concerns in physics, including the nature of dark energy and dark matter, which together account for a vast majority of the universe's mass and energy, but remain largely unknown. Despite being super elegant and promising, string theory has proven difficult to test. One of the major obstacles is that the more dimensions it predicts, the more minuscule they are, beyond our current capacity to observe. To identify these dimensions, we would need instruments of unprecedented sensitivity and precision. Even then, the evidence may be indirect. This makes superstring theory a challenging subject to test through traditional scientific methods. But its mathematical coherence and beauty make it one of the most compelling ideas in theoretical physics. At the same time, scientists are also working on other methods that could lead to breakthroughs in our understanding of black holes. For example, quantum gravity is another field of research that seeks to combine the principles of quantum mechanics, which govern the behavior of subatomic particles, with the theory of general relativity, which helps to explain the behavior of large objects like planets, stars, and black holes. It is hoped that by combining these two theories, scientists can gain a clearer understanding of how gravity works at the quantum level, resulting in deeper insights into the nature of cosmic phenomena, black holes in particular. The intersection of quantum mechanics and general relativity is especially important for studying black holes. The extreme conditions near the event horizon of a black hole, where gravity is extraordinarily intense, demand a theory that can account for both quantum and relativistic effects. The interior of a black hole, where the singularity exists, is one of the most puzzling and extreme environments in the universe. The singularity represents a point at which space and time are so warped that the usual laws of physics break down. Comprehending what happens in such a place requires a theory that can reconcile quantum mechanics and general relativity. This has resulted in the creation of concepts like loop quantum gravity and other quantum gravity models, which aim to resolve these inconsistencies and offer a more complete picture of black holes. As we continue to probe their mysteries, one thing is certain: the more we learn, the more we realize how much is yet to be discovered. Black holes are not just points of destruction, but also places of incredible complexity and potential. Whether they are gateways to other dimensions, as some theorists believe, or whether they hold the key to understanding the deepest secrets of space and time, black holes continue to be an important field of study. As our instruments and theories evolve, so too will our understanding of these enigmatic objects. Looking ahead, the next major challenge will be to refine our methods of observing and studying black holes. One of the most exciting advancements in recent years has been the development of gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the merging of black holes. By detecting and analyzing these waves, scientists can study the behavior of black holes and other celestial objects in ways that were previously impossible. The detection of gravitational waves has already provided groundbreaking insights into the dynamics of black hole mergers, and future experiments will likely yield even more information. In addition to gravitational waves, another promising area of research involves the use of advanced telescopes and imaging techniques. The Event Horizon Telescope, EHT, which produced the first image of a black hole in the M87 galaxy, is an example of how innovative technology can shed fresh light on dark matter. By combining data from multiple radio telescopes around the world, the EHT was able to capture an image of the black hole shadow, offering a glimpse into one of the universe's most mysterious phenomena. As technology continues to improve, it's likely that we will be able to observe black holes in even greater detail, revealing more about their structure, behavior, and role in the cosmos. Black hole research is not just about comprehending these odd objects in isolation. It is also about understanding the fundamental functions of the universe. Black holes are crucial to our understanding of spacetime, gravity, and the nature of reality itself. By studying them, we are not only learning more about these objects themselves, but also about the rules that apply to the universe at its most extreme scales. In conclusion, black hole research is one of the most exciting and challenging fields in contemporary physics. With each new discovery, we inch closer to unraveling the mysteries of these cosmic giants. Whether through the study of gravitational waves, advancements in imaging technology, or the development of new theories, black holes continue to captivate the imagination of scientists and laypeople alike. As we explore the universe's most extreme and enigmatic objects, we are forced to confront fundamental inquiries regarding the nature of space, time, and existence itself. And in doing so, we may be on the brink of unlocking some of the greatest secrets of the universe, perhaps even finding answers to questions that have puzzled people for millennia. As our journey into the cosmos deepens, we stand at the edge of a transformative era in physics and cosmology. The more sophisticated our instruments become and the more refined our theories grow, the closer we inch toward a unified understanding of the universe. This convergence of knowledge, where mathematics, observation, and imagination meet, is what defines the spirit of modern scientific exploration. Yet, with every answer we uncover, new questions arise. What lies beyond the observable universe? Could there be parallel realities, shaped by alternate physical laws, hidden behind the veil of extra dimensions predicted by string theory? Is the multiverse not just a speculative concept but a reality waiting to be proven? These questions are not only fascinating, they are necessary. They challenge the limits of human perception and push science to explore realms once confined to philosophical speculation. Even time itself, once seen as a linear and absolute measure, is now understood as something fluid, flexible, bent and stretched by gravity and speed. The possibility that time could behave differently under extreme conditions, such as near black holes or within other dimensions, opens the door to revolutionary insights into causality, aging, and even the potential for time travel. And then there is consciousness. Some researchers dare to speculate whether the fabric of the universe and human consciousness might be more interconnected than we realize. Could the observer play a more active role in shaping reality than previously thought? Quantum mechanics suggests this might be possible. And if so, understanding this connection could redefine not just physics, but the very way we understand existence. In truth, we are only at the beginning. Just as ancient astronomers once looked up at the night sky and saw patterns in the stars without knowing what they truly meant, we too are piecing together a cosmic puzzle with only fragments of the full picture. But unlike them, we now have tools capable of reaching the edge of space and time, and minds ready to interpret what we find. As we continue to explore, theorize, and discover, we carry with us a timeless curiosity, a drive to know not just how the universe works, but why it exists at all. And in the pursuit of that ultimate answer, we may find not only the workings of the cosmos, but a deeper understanding of ourselves.